V is subset are equal to V is subset are equal to capital Y. V is subset are equal to capital Y. By measurable rectangle in YA, YA, measurable rectangle in measurable rectangle in measurable rectangle in x cross y, x cross y. We mean R equal to we mean R equal to R equal to A cross B or A product B, where A belongs to script A belongs to script A, and B belongs to script beta, script B. B belongs to script beta, script B. Script B. Right. This is the product of measures. Product of measures. Then we'll prove a theorem. One theorem. Page number 53. Page number 53. Page number 53. Suppose XMU, prove that or show that. Question for question. Suppose the triplet X A mu and YB YBV YBV are complete measure spaces, are complete measure spaces complete measure spaces complete measure spaces. Then first one, the collection R of all measurable rectangles. The collection collection the collection the collection R of all measurable rectangles. R of all measurable Measurable rectangles. Measurable rectangles in a x cross y means product measures is a semi-algebra rectangles in product measure. Product measure means x cross y, x cross x cross y, x cross y, x cross y is a semi-algebra. Is a semi-algebra. Semi-algebra. Is a semi-algebra. Second bit. Second bit. If mu naught, if mu naught, if mu naught r minus r tends to 0 to infinity, 0 to infinity, 0 to infinity is defined by is defined by is defined by is defined by mu naught a cross b, mu naught a cross b, mu naught a cross b, that equal to mu of a, that equal to mu of a to v of b, v of a into v of b, v of b. For a cross b belongs to R, a cross b belongs to a cross b belongs to R. Okay. Next, a cross b belongs to R. Then for any countable collection of, then for any countable collection of, countable collection of, collection, a cross b, ai cross bi, a cross bi, a cross bi, a cross bi of disjoint measurable rectangles of disjoint measurable measurable rectangles, 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 measurable rectangles, whose union is measurable rectangle, whose union is, whose union is measurable, is the union is the measurable measurable rectangle A cross B, rectangle, rectangle A cross B, rectangle A cross B. Then mu naught A cross B equal to mu naught A cross B equal to I equal to 1 to infinity. I equal to 1 to infinity. Mu naught AI cross BI. AI cross BI. Next. Page number 54. Proof. Page number 54. Page number 54. Proof. Number 54. Proof. Proof. Case 1. First bit. First bit. Let R1, R2 belongs to script R. Let R1, comma R2 belongs to script R. Script R. So that R1 equal to, so that R1 equal to A1 cross B1. A1 cross B1. R2 equal to A2 cross B2, where A1, A2 belongs to A, where A1, comma A2 belongs to script A, and B1 and B1, comma B2 belongs to script B. Script B. So R1 intersection R2 is equal to R1 intersection R2. R1 means what? A1 cross B1 intersection. R2 means what? A2 cross B2. A2 cross B2. So that equal to, that implies A1 cross A2 intersection. B1 cross B2. B1 cross B2. Shows R1 cross R2 belongs to. This shows R1 cross R2 belongs to script R. Script R. Script R. Since A1 intersection A2 belongs to, since A1 intersection A1 intersection this way of this is A1 intersection cross B1 intersection B2. So A1 intersection A2, A1 intersection A2 belongs to script A, and B1 intersection B2 belongs to script B. Thus R1, comma R2 belongs to script R. script to R, and R1 intersection R2 belongs to R1 intersection R2 belongs to script to R. So equation number one. Equation number one. Here A cross B. Here A cross B belongs to A cross B belongs to R. Then its complement belongs to R. Then its complement 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 then its complement R complement R equal to A complement cross B intersection A cross B complement A cross B complement union A complement cross B complement that equal to S1 union S2 union yes yes where S1 equal to where S1 equal to A complement cross B S2 equal to S2 equal to A cross B complement A cross B complement S3 equal to A complement cross B complement A complement cross B complement A complement cross B complement A complement. Now A belongs to me since A belongs to script A and B belongs to script B. B belongs to script B. It follows that S1, S2, S3 are all the members of R. It follows that. It follows that S1, comma, S2 and S3, S1, S2, S3 are all members of all members of all members of script R. All members of script R. Script R. Script R. Thus R belongs to capital R. Thus thus thus, R belongs to, to R, so that equal to complement of R, equal to complement of R is complement of, is a union of finite, is a union of finite, union of finite collection of members of R, collection of members of R, collection of members of R. That is equation number 2 consider. So therefore R is a sigma, R is a not sigma, semi, R is a semi, therefore R is semi, 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 yes. So second bit, given A cross B, given A cross B, A cross B, union of I equal to 1 to infinity, union of I equal to 1 to infinity, AI cross BI, AI cross BI, where AI cross BI, BI intersection, intersection, AJ cross BJ equal to null set, equal to null set, where I is not equal to J. J. Fixing a point X in J. Embedding. Embedding means fixing. Fixing a fixing a point, beautiful point, yeah, in A. In A. We find that to each Y belonging, we find that each Y belongs to B. Each Y belongs to B. B. The point X comma Y belongs to X comma Y belongs to X comma Y belongs to AI cross BI. AI cross BI. A cross BI. For exactly one I. For exactly exactly one I, one. Therefore, B is the disjoint union of BI. Therefore, B is the disjoint, disjoint, disjoint union of those BI. Right? union of those bi, those joint bi for which x belongs to ai, which x belongs to ai, belongs to ai. And the countable additive of v, hence the countable additivity of v gives an uh, countable countable additivity ADI, BI, TI, additivity, TI, BI, TY, TY, additivity of V V gives, V gives, V of V, of V, Xi of A. This is treated as not X. This is Xi of A of X. Xi of A of X. That equal to sigma I equal to 1 to infinity. I equal to 1 to infinity. Okay. V of Vi, V of Vi, V of Vi. X, Xi of AI of X. Yeah, that implies, this implies integration, integration. V of B, V of B, Xi of A D, Xi of A, Xi of A, D mu, Xi of A, D mu, that equal to integration. X, integration. Sigma I equal to 1 to infinity. Sigma I equal to 1 to infinity. V of Vi, V of Vi, Xi of AI, Xi of AI. So D of, which can be written as, can be written as which can be, which can be written as, can be written as, written as, which can be written as, which can be written as, can be written as. V of V, V of V, integration, A Xi of A Xi of A, D mu, yeah, that equal to sigma equal to 1 to infinity, 1 to infinity, V of Vi, V of Vi, integration, integration, Psi of A, psi of AI, psi of D minus E, that implies, that implies V of B, V of B, V of A, V of A, that equal to I equal to 1 to infinity, equal to 1 to infinity. V of BI, V of BI, V of AI, so of AI, yeah, thus, thus, V of A plus B equal to not of mu not of A cross B, not of A cross B, that equal to sigma equal to 1 to infinity, equal to 1 to infinity, mu naught BI cross into BI cross, BI cross into BI cross. Proves the second bit. This completes the proof. Hence, so important for 10 marks question. Next definition. 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 E is any subset of E is any subset of any subset of E is any subset of X cross Y, X cross Y, and X belongs to X. X belongs to X by the X section of E. With the X section of E. X section of E. X section. We mean set. It is set E suffix X. E suffix X equal to Y such that X comma Y belongs to E. X comma Y belongs to E. Next. Similarly, E of Y, that equal to X such that X comma Y belongs to X comma Y belongs to E. X comma Y belongs to E. So next theorem. Using this definition, we can theorem 3, page number 55. Page number 55. Theorem 3. Theorem. Prove that if E belongs to, prove that or show that if E belongs to, E belongs to, E belongs to R sigma delta, R sigma delta, then Ex is measurable subset. Then Ex is measurable subset. Measurable subset. Measurable subset of Y. Measurable subset of Y. For all small x belongs to capital X. Small x belongs to capital X. For the meaning of R sigma delta. The definition 5. It belongs to sigma delta. With E subset B. So outer measure of E equal to outer measure of B. That means the proof. 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 If E belongs to, so first of all, E belongs to R. That E belongs to R. E belongs to R. Then E equal to A cross B. Means product measure. Then E equal to A cross B. A cross B means A cross B. Where A belongs to where? E belongs to script A. B belongs to script B. B belongs to script B. Script B. So that E of X equal. So that E of X. So that E of X equal to Y such that X comma Y belongs to E. X comma Y belongs to E. That equal to Y such that X comma Y. X comma Y belongs to A cross B. Belongs to A cross B. Belongs to A cross B. To A cross B. That means B if X belongs to A. B if X belongs to A. null set if x does not belong to A. Null set pi means if x does not belong to A. For any case, Ex belongs to B. For any case, Ex belongs to script beta. Page number 56. Script beta. Script beta. Then, does E belongs to R? E belongs to R. E belongs to R. Then Ex belongs to B. Then Ex belongs to B. Ex belongs to B. Equation number 1. We show that Ex belongs to B. We need to show that. Show that or prove that. Need to prove that Ex belongs to script B. Ex belongs to script B. Ex belongs to script beta. Script B. If E belongs to R sigma, if E belongs to R sigma, equation number 2, right? So in fact, E belongs to R sigma. In fact, E belongs to R sigma, then E equal to union I equal to 1 to infinity. I equal to 1 to infinity. EI where EI belongs to R, where EI belongs to script R, so that for any x belongs to small x, so that for any x belongs to capital X, E of x equal union of I equal to 1 to infinity, union of I equal to 1 to infinity, union of I equal to 1 to infinity. EI of equal to union of I equal to 1 to infinity, equal to 1 to infinity. EI of suffix x. Since EI belongs to R, since EI belongs to R, EI belongs to R, since EI belongs to R, we get EI of x belongs to beta. We get EI of x belongs to script R, script beta, script beta by 1, by equation number 1. Since beta is a sigma algebra, since beta is a sigma algebra, since beta is a sigma algebra, the union I equal to 1 to infinity, 1 to infinity. EI of x belongs to R. EI of X belongs to R. EI of X belongs to beta. Beta. That is E of X belongs to beta. Means E of X belongs to beta by 2. Equation number 2. So finally, suppose that finally suppose that finally suppose that finally suppose that finally suppose that E belongs to sigma delta. E belongs to sigma. E belongs to R sigma delta. R sigma delta. What is that meaning? Sigma delta means measure of A equal to measure of B. Meaning, by definition, previous chapter. Right? So that E equal to. So that E equal to. So that E equals. I equal to 1 to infinity. Equal to 1 to infinity. 1 to infinity. EI. Where EI belongs to R sigma. Where EI belongs to R sigma. R sigma. Then EX equal to. Then EX equal to. EX equal to. Intersection I equal to 1 to infinity. I equal to 1 to infinity. 1 to infinity. EI of X. EI of X. E of X. But by 2. By this equation equal to. E of X belongs to B. EI. EI of X belongs to script beta. Script beta. Since EI belongs to R sigma. Since EI belongs to R sigma. R sigma. For each I is greater than or equal to 1. Hence EX equal to. Hence EX equal. Hence EX equal. Intersection I equal to 1 to infinity. 1 to infinity. EI of X. EI of X. X. EI of X belongs to B. Script beta. Thus E belongs to. Thus E belongs to R. R sigma delta. R sigma delta. That equal to E of X. E of X belongs to script beta. And script beta. This completes the proof and proof. Important for 10 marks. Most important. Fibonacci theorem. Most important is Fibonacci theorem. Next theorem is Fibonacci theorem. Fibonacci theorem. Fibonacci theorem. Most important theorem. Page number 57. Page number 57. Fibonacci theorem. Fibonacci theorem. Fibonacci theorem. Sometimes they will ask the Fibonacci theorem. State and prove Fibonacci theorem. How to learn statement also. Let question formation is prove that or show that. So that let triplet x script a mu and y b b b complete measurable space. B complete measurable space. Measurable space. Complete measurable space. And fb an integrable function. And fb an integrable function. Integrable function. Integrable function. And product measures means x cross y. Then first bit For almost all x the function, for almost all x the function, almost all x the function f of x, y belongs to R, defined by f of x, y equal to f of x comma y is integrable on y, is integrable on y and integrable on y. Second bit is g of x equal to g of x is most important thing. G of x equal to y of db, is an integrable function on x, is an integrable function on x, function on x, g of integration g d mu, equal to integration x cross y, f d mu cross v is mu cross page number 58. Or more exemplicity, or more exemplicity, more ex- explicitly, 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 integration x, integration y, f dv, double integration, f dv, f dv, d mu, that equal to integration x cross y, f d mu cross v, cross v. Oh, oh. Easy and most important theorem. Leibniz theorem means theorem. If the theorem holds for two functions, then it is also holds for the difference. Therefore, it is enough to establish the theorem. In this case, f is non-negative. If f equal to x of e equal to x of e, where e is the measurable set of finite measure, where e is the where e is the where e is the measurable set of measurable set of finite measure with finite measure with finite measure with finite measure with e equal to a cross b equal to a cross b where a belongs to script a belongs to script b belongs to script b belongs to script b. Then f of x equal to xb. Then f of x equal to xb. It is integrable over y. It is integrable over y. Over y. Integrable over y. Since g of x equal to since g of x since g of x equal to integration y f of x comma y f of x comma y d of v of y that equal to v of e of x we get with previous theorem g of x is measurable function by previous theorem. G of x is a measurable function. G of x is a measurable function. Measurable function. Measurable function. G of x is a measurable function. Defined for almost all of x. Defined for defined for almost all of x. Almost all of x. Almost all of x. Almost all of and integration x g d mu equal to mu cross b of e mu cross v of e that equal to integration x cross y, x cross y, x of e, x of e, d of mu cross v, d of mu cross v, that equal to, integration x cross v, cross f dv, f d, mu cross v, mu cross v. So proving the theorem in this case, does the theorem holds in this case? F is a characteristic function of measurable set. F is a characteristic function. Characteristic, C-H-A-R-A, characteristic, characteristic, characteristic function of measurable set. Function of measurable set. Function of measurable set. Function of measurable set. Hence the theorem also holds in this case f is a simple function which vanishes outside the set of finite measure. F is a simple function. Is a simple function. Is a simple function which vanish finite measure. Which vanish. Vanish means to become zero. Which vanishes outside a set of finite measure. Outside a set of finite measure. Finite measure. Finite measure. Set of finite measure. So now f is a non-negative measurable function. F is a non-negative measurable function. Then there is a sequence pi n. There is a sequence pi n. A sequence pi n. Non-negative simple function pi n tends to where pi of n tends to f. F as n tends to infinity. Then tends to infinity. So pi of n x, pi of n x, less than or equal to pi of n plus 1, pi of n plus 1 of x for n equal to 1 to 10 for all x. Then the sequence pi n x is a increasing sequence of measurable function. Pi n of x is a increasing sequence. Increasing sequence of measurable functions. measurable functions, measurable functions, measurable functions of measurable functions of measurable functions, measurable 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 functions converging to f of x, converges to f of x. CGS means converges f of x. Therefore, f of x is measurable. Lebesgue monotonic convergence theorem. F of x is measurable. Measurable by Lebesgue monotone convergence theorem. So g of x equal g of x equal to g of x equal to integration phi of dv f dv phi of dv that equal to limit n tends to infinity integration y phi of n dv. And this function g of x is measurable function of x. And, and this function g of x and g of x is measurable function. Measurable function by Lebesgue monotone convergence theorem. Integration x g d mu that equal to integration x limit n tends to infinity integration y phi of n dv dv. So d mu that equal to limit n tends to infinity limit n tends to infinity integration x integration y phi n dv again dv d that equal to limit n tends to infinity n tends to infinity integration x cross y phi of n d mu cross that equal to integration x cross v cross f D. Mu cross V. So complete the proof of theorem, hence proof. Hence proof. Most important theorem in this chapter, 10 marks, then short question. Okay. Okay. So thank you very much.